So let's review real quick. We've gone through 2 passes now of the course content. Remember, we've got 3 big topics. What's a fluid, fluid statics, fluid dynamics. So in the what's a fluid section, let's talk for a minute about a key defining feature of fluids, which is the idea of viscosity. Newtonian fluid, the shear stress is proportional to the velocity gradient by the viscosity, which is a material property of the fluid. You can look it up in a table. And what this means is that depending on the rate of change of the velocity as you move away from a surface, we can calculate the shear stress. Our second time through the same material, what we did was we essentially got fancier. We said, well, what if things like this shear stress or this velocity profile change as you move around on the surface? If you wanted to find a force then, you'd have to start with some small area. Maybe this tau now is a function of the same coordinates that define the area. And so you'd have to integrate that over the area to get a force. Well, if you can do it for a force, you can do it for a torque just by looking at it acting at some distance r. And so we started defining these differential areas and using those to calculate differential forces. And those differential forces could be integrated to find forces and torques. We also looked at mass flow and mass, again, starting with some differential area or differential volume. We can integrate that. What that allows us to do is look at, say, the mass flow of a non-uniform profile where velocity or maybe even the density change as you move around in the area that you're interested in. Fluid statics is the study of fluids that don't move, and our first pass through we looked at the simplest version of that, which just says that as you move downward in a gravity field, the pressure goes up. And so we start with P1 being the pressure at the top of some liquid, and as you move down a distance h, P2 is just the original pressure plus a rho gh. If the top pressure here is atmospheric, then when you rho gh your way down, P2 happens to be the absolute pressure. But this could be all in terms of gauge pressure as well. And so anytime you move from one pressure to another, you just add a rho gh to get there. Second pass through, we looked at 2 applications of this principle. The first is manometers, which is just using delta P equals rho gh. We could measure h, and it serves as a measurement of the pressure. In addition, we have this idea of buoyancy, which just says, after a little bit of derivation, that the force pushing on an object by the fluid is equal to the weight of the displaced fluid. And so we can now find the force that's either causing something to want to float upward if it's in a fluid. Then we started letting things move. The first time through, we looked at the Bernoulli Principle, which relates pressure, velocity, and elevation. As long as it's an incompressible, inviscid flow, it's got to be steady, and we can only talk about points that are on the same streamline. So the big trick here is, if you look at this, if you were to write this between any 2 points on a streamline, you've got 6 variables: pressure, velocity, elevation, at each end of the streamline. And so if you want to use this, you essentially have to know 5 out of 6 of them right out of the gate. And so we use other principles like mass conservation or no-slip principle to find ways to eliminate unknowns as we use Bernoulli. The trick is in picking the best possible streamline to solve the problem. If we divide through by g, it makes it a very convenient form for using in internal flows, where every one of the terms now is in terms of some distance, which we call head or a height, and we add 2 extra terms to it here. One, head loss. This captures the effects of friction in a pipe, and pump head, which calculates the effect of adding some sort of a pump to our system. What's the head loss? Well, it's the pressure drop divided by rho g caused by friction. And so there's 2 ways we can find that. One is using the physically based formula, which says that we can take 4 tau wall L over d. Tau wall here comes from that mu du dy, and so you'd have to know the velocity profile to put this thing to use. On the other hand, we have the friction factor version of this, which is essentially just an empirical correlation. And so this business on the right, the L over d and the rho v squared over 2, are just scaled by some non-dimensional constant f, which you can look up on a table or a graph called the Moody diagram. And in general, it's a function of the Reynolds number and the relative roughness. And so we calculate these, we look up friction factor, that tells us the pressure drop. You can sub that in to this main equation here and answer all kinds of interesting design questions. Moving on to our second pass, we learned about minor losses. In addition to the friction losses, there are things associated with all kinds of other devices that show up in internal flows, things like bends and joints, T-intersections, nozzles, etc. And every one of them just has an empirical loss coefficient, KL, and so you can go look it up, multiply by the V squared over 2G. That gives you the head loss for that one item. And the beauty of head losses is that you can add them all together. And so this is just saying if you want the overall head loss, add up all the KL V squareds over 2Gs, and you'll get a single number for the head loss that can be subbed in along with the major loss, i.e. the friction loss, to get the overall head loss, once again, that can go into the head version of Bernoulli. When we move to external flow, this is flow over an immersed object. Our first pass through, what we said was that the lift and drag forces are the most interesting thing about them. And so, kind of like the friction factor, we can correlate them. And so we came up with the drag coefficient and lift coefficient, which are defined using some characteristic velocity and area. And we just simply go look up the drag and lift coefficients and invert those definitions to find actual lift and drag forces. Our second time through, we looked at the concept of where this came from, and lift and drag turn out to be the integral over the entire surface area of the object of the pressure and the shear stress. And so we can integrate those, they give us forces, and we define lift as the force perpendicular to the flow direction, and drag as the force opposing motion. We came up with some interesting boundary layer coefficients and characteristics, things like the boundary layer thickness and the displacement and momentum thickness. And these are kind of ways to generalize what we're thinking about. And we also looked at Reynolds number and how changing the Reynolds number changes flow regimes. Things like transition from laminar to turbulent, how things separate as you get downstream of an object, and what wakes look like. The big example there was the golf ball. And then lastly, we looked at kinematics. This is describing motion. We're not going to predict it yet, but we can describe it. So how do we do that? Well, first we start by coming up with a formalized definition of position, which is a vector r that has an x, y, and z component. We've put these t's in here to remind ourselves that every one of them can be a function of time. And so at any instant in time, a fluid particle could be in a different position. And we used unit vectors I, j, k to denote where that velocity vector or that position vector points. If you take the derivative of that with respect to time, we get the velocity vector, which is in general a position and time functioned item. And so we have here a x component, y component, and z component of velocity, which we call u, v, and w. And each one of those can be a function of position and time. So as we move around in the flow, the velocity can change as you go. Lastly, we talked about ways of visualizing this. The thing that's interesting about fluids is that their field effects can be non-uniform, and so we need some way to visualize this that's useful. And three ways to do that are the streamline, streakline, and pathline. In a steady flow, they're all the same, but in an unsteady flow, they're not. So the formal definition says that a streamline is tangent everywhere to the velocity field. And so if you pick a point, you can follow the velocity field by drawing a line that stays tangent to all the vectors. And the equation of that from similar triangles gives you this dy over dx is v over u. You can separate and integrate this to actually get the equation of a streamline, which is super useful when you're going back to apply something like Bernoulli. So if you had a velocity field, you could find a streamline, and then you could find you could apply Bernoulli along that streamline. A streak line is the collection of all the particles in a flow that have previously passed through a point. And so in an unsteady flow, this is a weird looking thing because it's some sort of zigzaggy pattern. It's just literally a bunch of little balls that have been tossed out into the universe, and we watch each one go, and you connect the dots, and that's your streak line. The path line, on the other hand, is the path of a single particle. So we launch a ball, and we look at its trajectory, and that is a path line. And so there are many path lines, clearly. they're defined just using the fact that the velocity is the derivative of position with respect to time, and so we can multiply up by the dt's, integrate these, and it gives us the equation of the line that defines the path of one fluid particle. And lastly, we came up with the idea of acceleration. And the thing that's interesting about acceleration is that because of the chain rule, you end up getting more than just the partial derivative of velocity with respect to time. When you do the chain rule, because the velocity is a function of position, we end up with these extra terms, this u dv dx, v dv dy, and w dv dz. This whole thing is called the substantial derivative. We use capital D's to represent it, and it has two components. This d by dt term, which is called the local derivative. It's the value at a single point, and it's equal to 0 if it's steady, right? Anytime something's steady, we get rid of the time term. But it's non-zero for an unsteady flow. And so this is, if we look at a single point, what's the velocity at that point doing? The remaining terms are called the convective derivatives, and they can be non-zero for both a steady and an unsteady flow. As you move with the flow, how are these things changing? So as we move with the flow, how does the velocity change? So you can imagine going along a streamline, that the velocity could change in any of these directions. That altogether is called the convective derivative. When we add that all together, it gives us a vector of acceleration. You can imagine we're very close now that if we have the acceleration vector, we can apply F equals ma to get some sort of physical prediction of the behavior of our system.